Hello, everyone. Thank you so much for being here today. My name is Madeline. I use she, her pronouns, and I'm with Cohere for AI as community and outreach specialist. It's my absolute delight to be supporting our research lab, particularly the community side of things. And today supporting two fantastic community organizers, Nahid and Harsha, who have volunteered to organize and present this presentation today. Thank you for being here. If you have any questions as we go, please feel free to put them in the Q&A at the bottom of your screen, and we'll get to them as makes sense in the flow of the presentation. Without further ado, it's my pleasure to hand things over to Nahid.
Hi everyone. Thanks for making time today. So I'm Nahid. You might have seen me lurking around the Cohere for AI community for some time. So I'm a computer vision engineer. I'm working at a camera company, so I'm very interested in building like sparse model, prune model. And we recently noticed in the community that there are other folks like Harsha and a lot of other folks who are interested in this similar space. So Sarah actually mentioned about Utku and his work in sparsity, especially on the, I guess, dynamic sparsity. So we decided to invite him. So maybe, I don't know, Harsha, if you want to introduce yourself, and then maybe Utku can introduce, and then we go from there.
Yeah, sure. So hi, I'm Harsha. I am a member of the Cohere for AI community as well. I mainly work at the intersection of theory, efficiency, etc., and deep learning. And I'm really excited for this talk. And it's definitely something that has been a really popular research topic, and more research is going into this area. So thank you to Nahid and everyone from Cohere for AI for helping set this up, and looking forward to it. Yeah. And Utku, you can go ahead.
Thank you. Thanks for, I guess, inviting me. And I'm following, I guess, Cohere for AI through Twitter, and it looks like a lot of impact and different people working on a lot of different things. It's good to see that in the community there's alternative paths, and yeah, I guess I would like to start with thanks for doing this, and thanks for inviting me. So while I share my screen, I'm a researcher, or it's already, do you see my screen right now?
Yes, I see.
Great. So I'm a researcher in Google Brain in Montreal. And I started with the residency after my master's at NYU, and I've been working on sparsity, sparse training particularly, and efficiency in the last 3-4 years. And yeah, like during this time, I got the privilege to work with a lot of amazing collaborators and publish some research, and I put their names here and to acknowledge them. So I won't be like, I think, actually I will be highlighting the individual collaborators in the projects, but just wanted to highlight here too. So maybe let's start it. So also, like, if you have any questions on any of these topics, feel free to interrupt me. I will be try to follow the chat. And also my voice is a little bit risky in the sense that I might lose it at some point. It feels a little weird. So if that happens, I might kind of become a little bit more silent towards the end. So today I would like to start with, so the title of the talk is Sparsity and Dynamic Training. So I would like to start with like the motivation and the usual question, why, and why do we want sparsity in our neural networks? This is kind of, I think, ill-posed in the sense that all of our neural networks are already sparse. You can take any neural network and convert to a one big RNN that is sparse, and that may or may not have parameter sharing, but it's highly sparse. So the question of like why sparse is therefore a little bit off, because again, like we don't connect all of our neurons to all other neurons, so it's only connected layer wise, and therefore like sparsity already there. So I guess the question should be like, why do we want more sparse than the existing neural networks? And the answer to that is the scaling curves. We observe that like larger neural networks get better results, and in return, that means that if you can make a neural network more efficient, you could actually increase your initial capacity to get to a better performance point. In a way, like by actually increasing the efficiency of your model, you are pushing your scaling curve towards a higher performance scale. So in a way, efficiency is equal to better accuracy. Thus, if you can make the existing network sparse, you will get better scaling curves. That means like for the same flops or for the same parameter count, you will get better performance. And this has been shown in the past, but just wanted to highlight a few papers here. One of them, the efficient neural audiences here, they show that, 1 second, I'll try to get the pointer working. Here they show that sparse networks, which is the right side of the plot, gets better negative log likelihood, so lower loss. And all of these points are networks with the same parameter count. So if you make your network sparse, you achieve better performance at the same parameter count. So this is for audio synthesis, and here a similar result for Roberta architecture. Here the curve that gets the best performance is a large model that is pruned with sparsity. So this better scaling is observed in different domains. I mean, I didn't put the computer vision here. That's the most obvious one. And this is the reason why we should think about like how can we make our neural networks more sparser. And the main question I think therefore we should be asking is the how sparsity. Like how do we want to introduce sparsity in our neural networks? And there's different dimensions. One is like you can have activation sparsity in your neural network. So these are data dependent, the data that is created through the neural network. And you have parameters which are constant, that are data independent. So you can introduce sparsity in both of these. You can have a static or dynamic sparsity. Again, like activation sparsity is more dynamic because it depends on data. In a similar way, you can think of dynamism through time. So you can change your sparsity pattern or amount throughout the training. So that's what I mean by dynamism, dynamic versus static. Again, you can think about like a constant parameter budget architecture, and with a constant budget architecture or without a constant budget, you can still think of like reducing, pruning, and growing operations as a part of the training recipe. In a fix, this could be kind of like reviving existing neurons. And if you don't have a fixed parameter budget, you can think of like increasing or decreasing your total network size through pruning and growing. You can have different granularity of sparsity. Like one big way of like introducing sparsity, removing entire layers. You can remove entire neurons. You can kind of think about blocks in your weight matrix and then sparsify them. And recently there's also like NM sparsity supported by the NVIDIA GPUs. There's different granularities, and as a rule of thumb, less structure you put on the sparsity itself, better performance you get. But again, this structure allows you to accelerate, and they're like more hardware friendly. And you can think of like single versus parallel paths. There has been some research again on sparse plus dense architectures. So you can replace existing layers with a family of sparse layers or sparse plus small dense layers. And this has been shown to be quite promising. There's the butterfly matrices, this from like Beatty, Tree from Stanford, there's this family of papers that are quite promising, and they use this like idea of parallel paths, and that is a quite interesting direction. And finally, like how do we distribute our parameter and computation across our neural network, across time in a way? And this is also quite important, like understanding that and understanding the principles there is quite important. So I worked on different parts of these questions. I mainly focused on parameters and dynamic sparsity. I worked on pruning and growing unstructured single, like pruning an existing layer or sparsifying an existing layer, and also worked on a non-uniform sparsity. But today I like to focus on this dynamism part and talk a little bit more about sparse training and then growing. So agenda today, I thought, and I feel like, given that we started a little late and in my voice, and it's already 15 minutes in, I think I might not be able to talk a lot about the last part, which is I will probably quickly mention, but the rest is there's still focus on this training part of dynamism, and I'll mention what do I mean by that in a few slides. So I would like to motivate like why dynamism is needed or beneficial, and then I will dive into some of my work or our work around sparse training, growing, and particularly applying sparsity in DeepRL. So let's start with dynamism, and I pasted this famous quote: "It is not the strongest of the species that survives, nor the most intelligent. It is the one that is most adaptable to change." Apparently, it's not a quote from Charles Darwin, maybe from Leon Megatson, we don't know. It doesn't matter. Like Charles Darwin has a lot of other great research. I've been like listening this book on where the innovations come from, and there's a lot of ideas, and a lot of those ideas include some kind of dynamism, mistakes, and variety brings kind of like improvements often, and or like innovations. And in a similar way, we can kind of think about like a neural network that is fixed and constrained to an existing architecture is less likely to discover like more novel ways of learning. And we can also look at our brain, like our brains kind of grow synapses, and then there's some pruning throughout our life, but there's quite a bit dynamism that in the way our neurons are connected. So there's all kinds of motivations for like why to think our neural networks, the need for thinking about neural network training in a more dynamic way. And we can have different ways of introducing dynamism in neural networks. One very maybe straightforward direction is the training itself. So we often have like these fixed structures, ResNet50s, VITs, transformers, and we often just train the parameters, right? Like we don't really change how the neurons are connected, and to me that seems like a big limitation. And in the past, and I will talk briefly, we applied this dynamism idea in a constrained way, but like in a like this inspired by this changing the architecture direction, we applied that to the sparse training and then improved the training performance. So this kind of like dynamism would be one way. And another one is the execution. So there has been quite a bit of work on sparse mixture of experts, so conditional computing. You can look at your data and then pick some of your parameters or modules that is most relevant to the data that you've seen. And that could help you to reduce your computation footprint. And another way that we can think about dynamism is like this deployment or recycling of the previous models or checkpoints. So we can also think this transfer learning or iterative learning ideas in this like dynamism way, in which we look our neural networks in a life where they may be pre-trained and then used and used again, and they constantly change. And some examples I put, I'm going to skip this because I already mentioned, so there's already some evidence in the literature that shows benefits of adapting such dynamic approaches to the neural network training or deployment or execution. And to summarize, so why should we care about dynamic neural networks? One is like, we probably we're not going to be able to find an architecture that will be perfect for all the tasks that we might want to use machine learning in. And obviously, one easy way of thinking is like, well, it doesn't need to be perfect. Let's kind of use transformers. It seems to be good enough. But if we can kind of figure out how to discover these algorithms in an efficient way, then like we could actually think about like finding the optimal architecture for each task itself, and therefore there is, I think, quite a bit room for improvement in that direction to kind of learn the architecture itself, but it needs to be efficient. And other one is like more for less. You can use these ideas to come up with more efficient optimization algorithms, and now this matters a lot. There's startups that focus on that, like how can we reduce the cost of our training, and dynamism could be one part of it. Like one easy example, you can start with a small architecture and grow that into a bigger one as a part of the training. So that's another way that we can use dynamism. And then finally, incremental learning. Like if you're thinking about like lifelong learning agents that learn from users or adapt to them, then we talk about like some incremental learning setting. And there, like you have to, by definition, be more adaptive, and only changing the weights probably not going to be enough. So there we will probably think about like new output heads, new input data, and some kind of adaptation that goes beyond parameters. And then finally, ideal, at least in my world, an ideal neural network algorithm should reach to AGI and should always improve given more data and in compute. However, in our current paradigm, where we have a fixed neural network, that is not possible, in the sense that there will be always a limit, that when time goes to infinity, our performance will be capped because of this limitation of fixed architecture. And the hope is maybe with this dynamic training direction is that like we can utilize this space of all possible architectures, and given more training or more data, we can get better results. So at least like guarantee that such improvement would be quite, I think, interesting.
There is one question.
I'd like to pause here. Yeah,
someone is asking, I think, on the chat is like,
I'm biased probably on my Twitter activity is probably a bit biased, but I've been following Mosaic ML, and they've been reporting quite a bit improvements on different training recipes, language models or vision, and there is, I think, more and more focus on improving that part of machine learning, which is like, even for research, if you run a bunch of experiments, and if you can run them more efficiently, or run 2 experiments instead of 1, those are great benefits. And I was pointing that out. Hope that answers.
One question I have from my side is, when we say dynamic sparsity, it's really on the training side, right? Like not after the fact.
Exactly. And I will talk a bit more about on that. And the dynamic sparsity that I will be talking about is exactly starting with a sparse architecture and training that efficiently. Cool. I will close the chats. And now I would like to dive in a little bit of the papers that I've worked in the recent past. The first one is this 2 papers. One of them we focused on, as I was referring to, this sparse training problem. And the second one is a follow-up on understanding that algorithm that we proposed better, and also understanding like why lottery tickets get good performance. And I will mainly focus on the first paper here, but quickly mention few key results from the second work too. So how do we find these sparse neural networks? I'm remove the slides for what do I mean by sparse networks. I hope that is clear to everyone. But we are talking about, let's say, a ResNet 50, and each layer, often every neuron connects to every neuron in the previous layer. And when we say sparse, it is going to connect only a subset of previous neurons. So there will be connections between neurons, and there will be some that normally exist, but we would prune them in the sparse network. So how do we get them? As I just say, you can start with the dense network and prune to get this sparse network. This is the brown curve here. This is ResNet 50 trained on ImageNet. You get pretty much the same performance at 80%. So you remove 80% of your parameters, and the performance decreases with higher sparsity, but overall it gets decent performance. And one observation made by various people, but like maybe became more popular by the lottery ticket hypothesis paper, was that if you were to train the same exact sparse network that is found by pruning from scratch, we don't get good performance. There's a significant performance gap, as you see here, between the pruned solutions and the sparse solutions that are trained from scratch. And lottery ticket actually initialization, which used the original dense initialization, helped this gap for smaller settings and with that uses lower learning rates. However, if you look at this at ResNet 50 scale, it actually doesn't matter the initialization itself, and this gap still persists. So in this work, we kind of ask this question: there's this huge gap. Can we train? And it would be nice to kind of bridge this gap. And we ask the question of, can we train these sparse networks from scratch, end to end, without ever needing the advanced parameterization and without sacrificing performance? So we want to be able to match this dense to sparse pruning performance. And the answer was yes. And we called this method rigging the lottery because we were able to make any sparse random initialization. And we could train any random sparse initialization to a good solution. And sometimes we even suppress the pruning performance. And the idea you start is the following. You start with a randomly initialized sparse network, and you train it for a while. And after a while, let's say every n steps, you reconsider the sparse connectivity in your architecture. Specifically, for each layer, you look at the weights that exist in that layer and prune a small fraction of them by looking at their magnitude. So if let's say we have 20% of the weights in that layer, we will remove 30% of that 20%, and then we will grow new connections. So in a way, like we rewire some of our neurons, and the total parameter count in the layer doesn't change during this. So we remove, let's say, 10 connections and add 10 new connections. And these new connections that are added, we find out that if you look at the gradients, you get significantly better performance than activating new connections randomly. And this gradient is calculated every n steps, and you don't necessarily need to store them. You only need top k. Thus, you can actually implement this efficiently without requiring like this full memory of a dense network. Therefore, like, since we train sparsely and the full gradient, dense gradient that we need is required by top k, which means that you don't need to materialize it, this algorithm is fully sparse. In a way, like if you had an architecture that supports fully sparse training, this would utilize it in the sense it will never need this full dense parameter budget or memory footprint. So this is the summary. I'm going to skip through the remaining because I want to also talk about the remaining of the slides. But we find out that if you train your sparse network with Wiggle, you actually learn to discover the right features. So this is the first layer in a flattened MNIST, and we visualize like number of connections from each pixel. And Wiggle basically learns to allocate most of its connections to the center of the image. And if you know MNIST, this is kind of where the information is, which is a cool feature. And if you look at this training flops versus accuracy curves, Wiggle does best compared to the other baselines and matches the pruning performance using similar amount of flops. And if you look at the, so this is for regular uniform sparsity. Another main finding in this paper was that if you smartly distribute your parameters across different layers, instead of doing like, if let's say 80% sparsity is my target, and I'm going to allocate 80% sparsity to every layer. That strategy is called uniform. However, you can actually do better by allocating more parameters to smaller layers and less parameters to the bigger layers in terms of percentage. And if you do that, this is kind of what ERK does, you get actually significantly better performance. So the purple curve at the top is better than the blue one. And actually, if you look at high sparsity regime, you get even better performance than pruning. So this is kind of like highlights actually end-to-end, the utility of end-to-end sparse training, and also more specifically, more importantly, the utility of dynamic training. So here, if you don't change the architecture itself, so you stick with the initial random sparse topology that you started your training with, then you get this suboptimal static line, which is significantly worse than the dynamic sparse training alternatives. And one last thing I want to highlight here was, so we always talk about pruning and efficiency, like we have this dense network, we kind of make it smaller without sacrificing performance. Another, the same thing, so the other side of that coin is keeping the total number of parameters same and increasing the sparsity and the width of your neural network simultaneously. By doing that, you can get like this wider network, but sparse network, wide sparse network that has same number of flops or parameter count as your original dense network. However, this network, due to being like wider, will perform significantly better. And this is being shown at by the last two rows. Here we have big sparse models. These are same flops as the original dense, and they get like 4% better performance, for example, on ImageNet. And this is kind of like, again, whenever we see efficiency, we should also kind of immediately infer that this also means better accuracy, because with the budget compute memory that you save, you can scale your neural network. And we know that larger networks do better. And thus, they are as important as improving. So I repeated that again. There is one more question from Diganta. Maybe I can pause for that.
Yeah, I could probably read it out for the others as well. Okay. Diganta asks, so sparsity as a keyword can be very ambiguous, is his comment. And sometimes these refer to weight sparsity or activation sparsity or that of routing-based mixture of experts. So Diganta asks if there's an established definition of what underlines sparsity, which is a pretty good question, I think. Yeah.
Yeah, I mean, I think if we look at and thank you for the question, firstly. And second, if you look at the vocabulary, I guess we will get a definition. And that is probably a good definition. Like, given a set of elements, only a subset of is active. And you can apply that to weights, you can apply to activations. And I talked about this at the beginning of my talk, like kind of when I was talking about how sparsity, it was activations versus weights. There is, I guess, like we should make it clear when we say sparsity, which one do we refer to? It was weight sparsity was very popular. So before, I guess it was mainly used for that, but now like we also think about activation sparsity. Yeah, I think we can just like append it by saying weight sparsity or activation sparsity at the beginning, and hopefully we can infer from that if we continue speaking with sparsity, which one do we refer. But I'll try to be more specific going forward when I say sparsity. But here, so far, I talked about weight sparsity. Is there more reason that sparsity leads to better performance than you can train more with your compute budget? Is in does sparse representations present data better within the network, gaining better performance? I mean, one reason that why sparse networks, so thanks, Max, for the question. I read the question, but maybe it wasn't good enough. I don't know whether anyone sees the chat, everyone.
I think
I kind of read it for myself.
No, it was good, I think. Yeah.
Okay,
so
great.
Go ahead. Yeah.
So Max was asking like why sparse networks does better. One obvious reason is the width. So you actually increase your width and increase the sparsity so that you have the same parameter budget, and we know that like wider networks, these are the scaling curves that we all know, brings better performance. So the wider network, more parameters, often given enough data will give you better performance. And that's the, I think, main reason why sparse networks does better than the dense. And apart from that, there is also some evidence that you can compare two networks. One is dense, one is sparse at the same width. So the sparse network will be more efficient. And there is some evidence for especially smaller data sets that sparse networks sometimes generalize better. And they even sometimes have better adversarial robustness. So I can't remember the name of the papers on top of my head, but there's a pruning survey, and maybe those are cited there, but there's some line of work that looks into these kind of characteristic at the same width. So like if you kind of compare two networks with higher widths, then obviously like higher width is a different, like it has more expressive. You can come up with, I think, ways to show this even using math. So, but like in the same width thing, even there seems to be some benefits to using sparsity in a way, like it's a better regularizer. It's a way to regularize your network. So that was a long answer. Hope that addresses it. Cool. Did I miss any other questions?
I think there was a follow-up question from, I think Jason also had a similar question to Max's. I hope he got his answer, but Diganta's asking, what is the intuition on why lottery ticket initialization doesn't work well when trained from scratch? I think the follow-up.
Yeah, I will answer that. I also see Jason has a question. Maybe I can quickly answer that one first and then go to the Digantas. So in this plot, the big sparse has same number of parameters as the dense network. So if you have uniform sparsity, this is the 76.4, it also has the same amount of flops. If you use the RK, you actually double your flops at the same parameter count. So all of these three models has same parameter count, but the RK has more flops because of the sparsity distribution. And it gets better performance, but like it increases the flops. So yeah, to answer your question, all these models have same parameter count as dense. And Diganta's question on why lottery tickets doesn't work on the ResNet 50. So we, in our follow-up work, gradient features, gradient flow, the chat box kind of covers the slide, so I was struggling a bit. Sorry about that. And in this paper, gradient flow in sparse neural networks, we investigated the initialization for sparse networks. So one thing that we realized is that if you have a heterogeneous sparsity, which means different neurons have different number of incoming connections due to sparsity, then you have to adjust your weight initialization so that you preserve the unit variance at every neuron. So this seems to impact the results a lot in earlier architectures like VGG or networks like smaller networks without like batch norm or skip connection tricks. However, if you go to this era, this more recent families of architectures and use them, you observe that the importance of initialization is less. All these tricks about batch norm and skip connections help you with training a lot. And even though your initialization may like often our initializations are not perfect, and that's completely fine. And that's what we also observed, that changing this sparse initialization didn't affect the results a lot at all, actually, in ResNet 50, for example. In those architectures, we find out that the gradient norm during early training impact the training results a lot. So Regal, for example, here you see a plot. We look at the gradient norm. We calculate the gradient of the weights and calculate the norm of that flattened vector. And if we plot that, we observe that Regal updates, you change the connectivity, increases this metric early in the training. And that correlates with this better performance that we obtain. However, as I said, like changing the initialization doesn't help. And to answer Diganta's question, lottery tickets doesn't work because this ResNet 50 architectures have such a high learning rate, and they are optimized so that those big steps doesn't affect your overall optimization. Due to those like large steps and tricks that manage to keep the training in place, initialization is kind of irrelevant because you have this catapult steps at the beginning that makes you jump a lot, and the individual initialization doesn't matter at all. And maybe like another thing that I can say to answer that question is this final key result from this work, which is we looked into the similarities between lottery solutions and the pruning solutions. If you're familiar with the lottery ticket initialization, what it does is it makes a pruning run. So you start with a dense network and prune that dense network during training, and you get a pruning solution that often performs really well. If you remember the curve with the brown results, so that's pruning, that does really good. And what lottery ticket does is like it gets the mask from this solution. So this is the same connectivity pattern in that network, and uses the initialization used for the original pruning experiment. So the exact initialization used for that dense network, and apply the mask that you find through pruning, and you get a sparse initialization, right? And if you train that, you sometimes get good results. And what we did is we looked how similar this lottery ticket solutions and the pruning solutions are. And what we find out is the distance-wise and the function similarity-wise, these two solutions are kind of next to each other. In a way, when you apply this mask found by the pruning solution at initialization, you nudge your initialization towards this pruning solution that you found. And if your learning is such that you don't jump a lot, or your initial learning rate is not high enough, you are able to relocate this basin that includes the good solution. And lottery ticket works if it can refines the pruning solution. And it doesn't if due to large learning rate, you maybe like jump, for example, in ResNet 50, maybe you start like this, but due to large learning rate, you jump to this like other parts of your energy landscape, and you are not able to find your pruning solution again. And so that was a long answer. Hope it answers. Okay, so we have 18 minutes. I will continue. The second work, so far I talked about random sparse networks trained dynamically using gradient information, and all of this work was about the connections, the edges between neurons. And in the next work, we kind of looked into, can we use this idea of maximizing gradients or improving the gradient flow during training to dense neural networks? So can we grow neurons so that our overall gradient norm is increased? And that led to this work that we called GradMax, gradient maximizing neural network growth, which we presented at ICLR last year. And the motivation for growing is the following. I kind of already mentioned part of it for the motivation for the dynamism, but continue learning where you learn new tasks. Ideally, you want to also grow new capacity. So progressive nets is one example where you increase your capacity throughout your learning process. Secondly, you can use growing in a architecture search setting. You can think of like starting with a seed architecture and finding the best places to add new capacity, and by doing that, you can hope to achieve or find better architectures. This is, I think, an exciting work that could enable this ideal setting I was talking about, where you optimize the architecture and the weights together, so that like when you train longer, you always get better results. And finally, you can start with small architecture and grow it. And this has been used actually widely, I think, more and more, especially with very large models. People often don't train it from scratch. And if something changes, people often warm start with previous checkpoints and results, and often grow new capacity whenever needed. And this helped, for example, OpenAI in the Dota 2 project to be able to experiment and reduce the overall project time. So the existing work in growing can be grouped under two categories. One of them is splitting. So if we have a neural network, a toy one, that has two neurons in this layer, we can think of splitting as copying one of the existing neurons or group of neurons, and then adjusting the outgoing weights so that the sum of these two weights equal to the original outgoing weight. So this will be the same neuron duplicated, and so the network will produce the same thing, but now you have more capacity. And often you add a small noise to these identical neurons to kind of break the symmetry. However, as you can see, there's like a lot of repetition, right? Like you create new neurons that does pretty much the same thing as other existing neurons, which is often like not an ideal thing to do. And other family adds new neurons that are independent and ideally orthogonal or like somehow orthogonal to the existing neurons. And there is some work also on this previous work, and in this work, we will focus on this adding because of that limitations I mentioned about splitting. And also, like in our experiments, we see that the adding is a better strategy than splitting. So the motivation here, we will try to maximize the gradients. So we will add a neuron and we will try to maximize the gradients through this like new added capacity. One thing that we want to do is like, we don't want to change the output of this neuron, which means we're going to make sure either incoming or outgoing weights are zero. And again, which means that we're not going to be able to change anything, including weights and gradients about the existing capacity. So the only thing that we can maximize is this new capacity that we are adding. And here I like to quickly motivate why maximizing gradient is a good idea. It comes from the Taylor approximation. So if you change your weight slowly, which means in our deep learning setting, a small learning rate. If you have a small learning rate, you can fit a quadratic model and think about like this minima as the combination of your existing loss plus a term that that depends on the gradient itself. And when you maximize the gradients, you basically increase this term, which means you're decreasing this loss value at the minima. And in other words, you are guaranteed to get better or smaller training loss in your next iteration. Everything else being equal, if your gradient is larger, you will decrease your loss faster. And obviously this is for one step, and we often take multiple steps in our training. So the key here is like improving gradients throughout the training. And our hope is like, if we can maximize gradient during this growing steps, that will sustain for a while. And overall, we will get a faster optimization. And I mentioned already this. So specifically in GradMax, we will set incoming weights to 0 because this has like this nice property where your activation is 0. And if you apply nonlinearity, you already know it is going to be 0, like depending on which activation, but like there's some nice feature about your activations being linear. And we will optimize the outgoing weights such that, so this is the optimization basically we are doing. We will maximize this value by choosing the outgoing weights. And this value that we are optimizing is the gradient in incoming weights. And why that is the gradient at the outgoing weights are 0 due to this 0 activation. So the only non-zero gradients are in this incoming connection site. And we will also want to have a fixed norm for the outgoing weights, because by changing this norm, you can arbitrarily maximize this part. So we want to fix the norm of the outgoing weights. And in this paper, we show that like this problem reduces to a spectral problem where there's a matrix that we can efficiently calculate. And if you calculate the top k eigenvectors of that, so there's a typo here, it should be eigenvectors. So the top k eigenvectors of this matrix is equal to the optimal initialization for outgoing weights that maximizes this gradient for a fixed norm. And since like we set incoming weights to 0 and like the rest of the network doesn't change due to this 0 initialization, we can solve this spectral problem independently for each layer, which is parallelizable, which is a very good property. And sometimes in certain settings, actually, this closed form solution doesn't exist. Like one example is like if you were to set outgoing weights to 0 and initialize the incoming weights to a non-zero value, then this closed form solution doesn't work. And in such settings, we can still use the same idea, same optimization problem to come up with an initialization. And we do that by using like regular gradient-based optimization. You can optimize this value using automatic gradients, or like any your favorite neural network library. So our experiments starts with this toy setting where we have student-teacher networks. So you have one network, 2-layer MLP initialized randomly, and that generates the data. And there's another randomly initialized student network with the same architecture that tries to learn from the data that the teacher created. And the nice thing about this setting is that if the student can learn the weights of the teacher, it can actually get 0 training loss. So there is a global minima at 0 in terms of training loss. So this is a good thing. And here we have different experiments in this setting. And first we look into the gradient norm after the growth. So we measure the gradient norm after growing capacity and observe that indeed grad max get the best performance. We compare it with random. The optimized version improves over random. However, it is not as good as the closed form solution. And if you look at the gradient norm over the course of the training, it kind of goes up at the time of growth. So here we grow 5 times at 200, 400, and the gradient norm decreases. However, it is sustained higher compared to the random, which is a good thing, which is what you need to really get a better training loss. And we can also see this with the how much loss improves compared to the baseline of growing randomly. We have this full training curves where this gradient-based growth does better than random. One thing that I want to highlight here is that like you start with a smaller architecture, which is this green curve. I think that in this case, it has 5 neurons at the beginning. And there's this teacher architecture, which is you start from this green in a way and grow it into the red, this larger architecture, which has 10 neurons in the hidden layer. And ideally, the grown architectures should match this red curve. However, what we observe is in smaller architectures, this is not the case. So there's this gap that we should be able to bridge, but even the gradient maximizing initialization doesn't entirely solve. It improves over random, but there is still this gap. This gap doesn't exist for this larger setting. And we also have ResNets, VGGs, MobileNet on CIFAR and ImageNet datasets. The improvement over random is marginal. There's 0.5% or 1% improvement, which is not great. But more importantly, there seems to be a big gap still between the grown networks, which are all these 3 lines here, and this big baseline, which is the training the large network from scratch. And ideally, these curves should match this one, as I said. So there seems to be some, I think, exciting and important research to be done to understand how can we, like why this happens and then bridge the gap itself. So this was GradMax. naive initialization. So given that I have 6 minutes, I will just maybe say one thing about this work. So recently, so here it says soon at ICML, I guess that passed. So we presented this work at ICML this year. And the motivation was that all the works that I talked so far, and most of the research in sparsity, is done in computer vision. And this is a little troubling because computer vision is already we are very good at. And a lot of problems in the world, like this is one piece of the very big puzzle, like the kind of things that we can use machine learning at. Computer vision is, I think, a small piece. And if we do all of our baselines and benchmarks in this domain, we have this danger of overfitting our algorithms, our recipes towards this. And one thing we wanted to do is to apply and compare these sparse training and pruning methods in deep reinforcement learning, and that's what this work is about. So we apply sparse training algorithms, dynamic sparse training algorithms, static sparse training in different RL environments. And I think RL is quite interesting because of this challenging training dynamics. The data distribution changes over the course of the training, and I think it is more realistic than the computer vision classification tasks that we all love and use. So there is a need for, I think, applying these algorithms to more realistic settings. And hopefully this work was one step towards that. And we use like these methods, and maybe just pause in the slide for a second. What we observe is if you use non-uniform sparsity, and that was the key thing that changed the performance significantly. So if you played with RL, and if you look at this architecture used in RL, there's a lot of imbalance between how large the layers in the middle are compared to the first or last layer. And often in the past, when people prune these networks, they uniformly pruned all layers. And when we applied ERK, this distribution that I mentioned that allocates the weights more wisely, we observed significant improvements. And in SAC, in Mujoko, and in DQN, in Atari, we were able to match the original dense performance with 90% sparsity on average. And before it was around 50%. So this is kind of like good news, I guess, for sparsity. And secondly, we had this surprise result on ResNet backbone and DQN algorithm trained on Atari, where actually pruning improved results significantly. So this is the original dense baseline. We pruned 90%, and we were able to get like almost double or like 50% better results compared to the dense network. So this is both smaller, but also somehow it got better results. So this is something that we are also looking into now. But hopefully this highlights the importance of like thinking of and using different domains in research, and you might be surprised actually with the results in a good or the bad way, and both are important for improving our methods. So I will pause here. There's last 2 minutes. There's questions, and maybe I go to my last slide. Yeah, today I didn't talk about head to toe, but this is more about like structured sparsity applied in transfer learning. So feel free to check that out. Talk about Wriggle, which is dynamic sparse training algorithm, GradMax, growing neurons. And hopefully these, and there's a bunch of other work too, that motivates the promise or importance of dynamism in our research and in the training of neural networks. And similarly, the importance of sparsity. And yeah, feel free to follow me on Twitter. And I would like to conclude with, it's not a single ResNet transformer or mixer that survives hard remove. It will be a dynamic neural network that is most adaptable to change, I guess is my prediction. And with that, I would like to conclude, and maybe I can take the questions. Thank you.
Yeah, I think there was one question a little while back by David, which we could start with really quick. The question is there any overlap, correlation, etc., of parameter signs in sparse architectures and the initial dense architecture? And is there any work generally on that? So I think that was the
Yeah,
question.
I think it is called supermask. So Hattie, okay, I cannot, but yeah, so there's this work from Hattie and others from Uber AI, which I think ceased to exist. You can look into that work. There is some correlation indeed. No, wait, it's not no, it is supermasks. Let me find the name of the, yeah. It's called Deconstructing Lottery Tickets. So there seems to be some correlation in the lottery ticket setting. And that is, I don't exactly remember their conclusions. I guess probably best to check that. I don't know how to send a message. I can send it to Backstage, it looks like.
Yeah, I could reshare it on chat really quick.
Perfect.
Yeah, I think it
Yeah.
go ahead. Yeah. And I think the next question would be by Jason really quick is, do grown networks here end up with the same architecture as that of the baseline? I think assuming the papers that was,
Yeah, in that paper, yes, we wanted to really focus on the effect of growing. So we kind of had a fixed schedule on where the neurons are grown. And yeah, so the all architectures in that plot, especially at the end. So you start with a small architecture and grow that small architecture into the same big architecture. And at the end, all of the grown architectures and the big baseline has the same architecture.
and I believe the last question, if we have time, is Diganta asks if you could highlight how GradMax doesn't violate probably.
So doesn't violate normalization, meaning it is the unit variance. So for batch norm, you can initialize it. So in the batch norm, the tricky thing is like if you have a zero activation, batch norm will go nuts. Like if it's always zero on connectivity, so now you have zero variance and it will try to scale it and that won't work, and the epsilon used in batch norm will kick in. And that will also mess things up for the gradients because you will divide things with that epsilon, and that means you will also divide your gradient with epsilon. So what we did, and there's some fixes you can do for that, but for batch norm experiments, if I remember correctly, we did the other way around actually. So we set the incoming weights so that the gradients in the outgoing weights are maximized. So the outgoing weights are zero, and we maximize their gradients. And in that setting, it's just like your neuron will have some activation and it's going to be normalized with batch norm. That doesn't work with layer norm, as you may imagine, because layer norm normalizes using all of the neurons. And if you have a non-zero neuron, that will affect and change your function. So we discussed all of these basically in the paper, if I remember correctly, in the appendix and in the main text. So there are ways of keeping the function itself, and some of them works with the closed form solution GradMax, and if it doesn't work, we do the optimized version of GradMax. Thanks for the questions again, everyone. Thanks for joining.
Yep. Thank you so much, Utku. And being under the weather and still joining in, it was an excellent presentation. At least as someone who also works in this area, I got a lot of inspiration. I'm sure it's for the others as well who are interested in the general topic. And thank you so much for joining once again. And yeah, that should be all. Over to Madeline for any other points.
Thanks for coming, and thank you so much, Utku, for this thorough presentation. well under the weather. Discussion and such good engagement from our community. So I think everyone's walking away with a little bit more to think about. Have a great rest of your Friday, everyone.
Yeah.
Thank you, everyone.
See you.
Bye for now.